be giving bonus lectures about the relationship between Legendrian links and blur theory. So this is a story that can be told independently of what Roger is doing in his main lecture series, but really they're quite closely intertwined. And the intertwining will probably not happen today, but I'll try to talk about them in the second lecture, which will be on Friday, I think. I want to start with an apology. So the apology is for those of you who are quite familiar with Legendrian contact homology. Today is going to be just essentially an introduction to Legendrian contact homology and and so if that is you and you're bored, you're welcome to do your own thing or storm out or watch TikTok as long as you can do it. Apology is that I'm going to be sweeping lots of details under the rug. So if something seems not quite right, it's probably not quite right. Okay, so I'm going to try to deal with the simplest possible setting, and so the setting. So the setting is going to be standard contact R3, which I think Roger was just sort of assuming that we're all friends with. Is that true? Are we all friends with this? Should I say so? Should I say something about the front and Lagrangian projections, or is this? I'll say something. Nobody is going to volunteer that I should either say something or not. So okay. So the setting is going to be this is the kernel of the Roger was using lambda. So this standard contact one form is going to be dz minus y dx. I'm going to be talking about a Legendrian sitting inside of this. Most everything I'm going to do today in terms of examples will actually be nods. So when I say link, I mean not the link. And I think for various contexts, it's actually maybe useful for it to be oriented. So in Roger's lectures, the links were always the Legendrians were co-oriented. Oh, well, the fronts were co-oriented. Here I actually want to choose an orientation on each of the components. And so in this setting, there are two useful projections, ways to depict this. So there's a front projection to the MC plane, and then there's the Lagrangian projection, complex projection. XY plane. The front projection, this is the sort of stuff that you'll seen already. So over there, there's this picture of the trefoil. And I think as you all know, you can recover the y coordinate by setting y is equal to dz by dx. And that means that at these double points, we actually know which is the overcrossing and which is the undercrossing in this projection. It's always the one with more negative slope is over the one with more positive slope. So this is the trefoil. The Lagrangian projection is projecting to the xy plane. This is, if you're just dealing with these and you want to play around with these things, it's usually easier to deal with the front projections than the Lagrangian projections, even though the Lagrangian projection is actually non-singular, so it doesn't have these cuspidal points. It's actually an immersion generically. But the problem is that it's not always clear from a diagram whether it actually corresponds to a Lagrangian projection or not. The point being that to recover the missing coordinate z, you have to integrate y dx, and then there's some subtlety about crossing information areas and that sort of thing. But for Legendrian contact homology, which is what I'm going to talk about today, it's much more useful to do things in the Lagrangian projection for reasons that maybe I'll touch on as we go along. So it's useful to be able to start with a front projection and end up with a Lagrangian projection of, if not the exact same Legendrian link, at least something that's isotopic to it. And so there's a procedure to go from front projections to Lagrangian projections called resolution, which just takes, so every double point crossing the front projection, you just do this. So that's actually sort of already done. But then what we do to smooth out the cusps is every left cusp we smooth out like this, and every right cusp we smooth out like that. And then it's not too hard to show something that I wrote down a while ago, but it's sort of a nice exercise if you haven't seen it before, is that if you start with a front projection of some Legendrian link and do this combinatorial procedure to get some sort of, oh, maybe I should do it there. So. Actually, I want to do a slightly different thing. So this will look more like a Weaver closure. Here's our from the trefoil again. So if you do resolution to this, what you end up with this. And there's a result that says that when you do this resolution procedure, that the end result is actually the Lagrangian projection of some Legendrian link, and that furthermore it's Legendrian isotopic to what you started on. And if this is too far down on the board, it's also over there. Okay. Okay. And what we're going to be focusing on in a second is the crossings in the Lagrangian projection. These crossings, so the crossings in the Lagrangian projection so these are what are called grid chords. So these are integral curves, or corresponds to. Of course, so these are integral curves for the relative vector field. So I think probably most of you know what this is. If not for our purposes, it's just the vector field in R3, which is just pointing in the z direction with endpoints on lambda. So you can see that if you projected away the z coordinate, then these crossings exactly you can join the top and the bottom of each of these crossings by a line segment that's just in the z direction. So that's exactly one of these things called a grid chord. Okay. Great. So I debated what order to do these in, but I think what I'm going to do is I'm going to just dump on you the definition of Legendrian contact homology combinatorially. Which has the advantage that it's maybe a little bit easier to parse and also more useful for what you all will actually want to think about this for. But it will sort of come out of nowhere, and then hopefully at the end of today, I'll have some time to give the geometric motivation for what we're doing. But for now, I'm just going to pull this out of the hat. So, what is this combinatorial definition of? It's actually of what's called the kind of Ashberg differential graded up. Which I will never again write out because that's just way too hard. Okay. So this is going to be some complex that's associated to a Legendrian link inside of R3, whose homology is what's called Legendrian contact homology. Discuss this in a bit. Okay, so let's start with the XY projection, the Lagrangian projection. Legendrian link. And again, so the crossings in this projection are what are called grid chords, and I'm going to label this. So we'll label the crossings. I'm just going to give them names. I'll call them A1 through AN if they're n of them. And I'm also going to choose a base point on each component away from the crossings. And I'll label these maybe T1 through TR, where R is the number of components. I'm going to be doing this example over here, which is hopefully visible as a running example. So this is a case where we have 5 rave chords and 1 component and 1 base point. So I've suppressed the subscript on the T. There we go. So the Chekhov Eliashberg differential gradient algebra is defined by. So I'm going to do it in 3 stages. I'm actually going to do it hopefully properly enough that we can actually do the computations yourself if you want. So first I'll tell you what the algebra is, then I'll tell you what the grading is, and then I'll tell you what the differential is. So the algebra, this is going to, well, this would upset the earlier version of B, which was a purist about these things, but I'm going to allow everything to commute with everything else. So this is just going to be a polynomial ring. K is n equals. But for the earlier version of me, let me just put in this. Usually one does this and does not allow things to commute. So usually let's do a non-commutative algebra. But I think for the purposes of what we're going to be doing this week, it's enough. It's fine to allow everything to commute. So I'm just going to do this so I don't have to worry about orderings of stuff. Okay.
Does it need to be super commutative for the gradient to still have?
Oh, yeah, good. Yeah, I guess I should probably make it be super commutative. But since I haven't described the gradings yet, maybe that doesn't make sense. But yeah, once I've graded things, then things should commute up to a sign which depends on their gradings. Okay. So that's the algebra. That's easy. The grading. So what I'm going to do is I'm going to describe the grading for AI. So again, crossing. I think with this data that I've given you here, there exists a unique thing which I'll call a capping path. Long, so gamma I lambda from the bottom to the top of word AI. So AI is it's one of these crossings here. It has a bottom and it has a top point, and we just join them along lambda. And what will make this unique is I'm going to make this avoid all the base points. Oh. Okay, okay. Let's assume for simplicity that lambda is a knot. So you can do this in the link case, but you have to be a little bit more careful. So what's going to happen in the link case is that some rave chords will have endpoints that are on different components, and so there's clearly no way that you can travel along the Legendre itself and get from one endpoint to the other. So what you have to do is go from one to the base point on that component, then jump to the base point on the other component, and then go around. If you want to see this written out in gory detail in the Lagrangian projection, you can. My L infinity structure paper from a couple of years ago has this in it, but it's not. Somehow I think all of the interesting stuff is already here in the case, so I'm just going to assume for simplicity that this is enough. So for instance, let me give an example. A1. I think there's something that goes, what did I say, from the bottom to the top?
Yes.
I think it goes like this. This is. Okay, and now this capping path inside of R2 has a rotation number. So I'll write this as R gamma I. And what this is the number of counterclockwise revolutions. By the derivative of gamma I from beginning to end. So I was sort of assuming, I never actually said this, but I'm gonna assume all crossings are transverse. This is some genericity condition. And so what that means is that the direction that we leave a crossing in and the direction that we come back to it at are, they don't coincide with each other, and they're also not opposite of each other. So that if you just follow the path from the beginning to the end and just look at how its derivative as a point in like S1 rotates around, from beginning to end, it'll do some number of rotations, which is neither an integer nor a half integer. So let's do audience participation. So what do we think it looks like here?
Minus a quarter.
So like minus a quarter? Yeah, so if we're assuming that this is orthogonal, which it doesn't have to be, but let's assume for simplicity, then I think it's about minus a quarter. So it's- Okay. Okay, and so the grading then of AI, so define the grading of AI to be equal to oops. Polar function and minus signs are what? So if you take twice of that number, that is not an integer, and I'm just going to take the negate it and then take the floor of that. That looks a little bit weird, but this seems like to me like a pretty nice general way to define this. So in this case, for instance, the grading of A1 is 0. So this works to grade all of the AIs, and then the T's. Well, I was assuming that lambda is a not, but I guess for this part, I'm going to state it more generally. So TJ, this is by definition, this is minus twice the rotation number of the entire component lambda j. So this is the entire. This is a rotation of the entire TJ of lambda j. Sorry, that's too far in the board to be visible, but what I mean by this is each component lambda j, you can get a path like this, just go all the way from the base point back to itself, let's say. And so if you count the number of counterclockwise revolutions, that actually is an integer. And so I'm taking that integer, multiplying by 2 and putting a minus sign on. So this actually does depend on nothing so far I think has depended on the orientation of the Legendrian, but this one might. So okay, so that's the definition of the grading on here, and I guess the base field itself is in grading 0. And if you do have this particular example, what you end up with is, so the example A1, A2, A3, and T are all in grading 0. So if T is in grading 0, that means that T inverse is as well. And A4 and A5 are. Great. Any questions about this? I'm sort of pulling this out of thin air, so as long as it's at least sort of understandable what the definition is, that's. Okay, so the differential.
I'm not asking about the details of this, but
Yes.
does this come from an index with an operator?
These are Conley Zander indices.
Okay.
Associated to the inputs. For the gradings of the A's and for the T's, that's that's the rotation of the. Okay. Okay, so the differential, so this is the part that's always a little bit trickiest to do because to write it down formally, it's easy to make your eyes glaze over, so I am going to write it down formally, but then hopefully we will quickly pivot to an example, so I think a number of you have already seen this before, and then this will be fine, and if you haven't seen it before, just a little bit of patience and hopefully it makes sense. So, given a collection of grade chords, which I'll write as AI, AJ1, AJK, a collection of at least one grade chord, so AI along with some possibly zero number of other ones. I'm going to define something I'll write as M. A1 thing. So so far this isn't actually terrible. So what's DK2 is just a 2-disk, but with K plus 1 punctures on its boundary. So just remove so it's U2 minus K plus 1 boundary punctures. And what's going to happen is that this disk is going to be mapped into R2 in such a way that its boundary is maps to the XY projection of random. Oh. In this setting, I actually don't need to remove the boundary punctures, but maybe it's better for the geometric motivation later on. Okay, so that's not so bad. The key is this thing that I haven't told you what they satisfy. So this is several things. So one of them is actually okay. So these boundary punctures are sent, or neighborhood of the boundary punctures are sent to, maybe I'll say boundaries. To AI. Okay. So that is to say that there's actually there's a way to continuously extend this to a map from the closed 2-disk into here, so that these things that I removed before are now being sent to AI through AJ1 through AJK. And what's the neighborhoods? So the boundary point is sent to a quadrant as the relevant crossing. And now I need to say, so so each crossing looks sort of like this. And what I will do is, so at this crossing, there are 4 quadrants, 1, 2, 3, 4, and I'm going to decorate them with signs. So decorate. Decorate. Quadrants. By these signs. And then which quadrants a neighborhood of each boundary point gets sent to will depend on whether it's AI or AJ1 through AJK. So it needs to be a plus quadrant for AI and a minus quadrant for the others. Um, yeah. Again, we will do some examples in a second, but I want to actually give the definition of the differential. So again, this is going to look sort of hideous. Um, Okay, so basically I'm summing over all possible ones of these are M tensor moduli space, but these moduli spaces where I let this part that comes after the AI change. So the immersion is going to look, it's going to cover a positive quadrant at AI, and it's going to cover a negative quadrant at some other things, but those other things can vary. So I'm summing over all possible ways to do this. And the simplest thing to say is that I'm just going to write down the words that it's just the negative, sorry, the quadrants that have minuses on them. But then there's some decoration in front of this, which I'm writing as W delta, where almost there. So now I need to tell you what the sign is and what the thing. So NI of delta is the number of times the sign that's the boundary of delta passes base point Ti. And the sign up here is the product of what are called orientation signs. The quarters of these quadrants, and I will color code this somewhat differently from over there with orientation signs. So each of the quarters where one of these quadrants is covered will have an orientation sign on it, but they're different from the signs that are written over there. And what they are is, so at a crossing, the crossing could be a positive crossing or it might be a negative crossing. This is a positive crossing, that's a negative crossing. And the orientation signs are minus, minus, and everything else is a plus. So the key ones here are there's a minus, minus here. And you just multiply together all the signs at all the corners, and that gives you a plus or minus 1, and that's the fun. Let's do it easy. with D of A4. In that example over there, there are 4 terms in this. So I'm gonna try to write them down for you. So, what these look like is there's a disk that looks like this. So it's just that little loop up to the right of A4, so there's a map from a disk with a single boundary point on it to this, where the boundary point gets sent to A4. A neighborhood of that boundary point gets sent to this quadrant at A4. Okay. Great. So that's that one there. Oh, and so what is special about this one is that there are no negative corners. And when there are no negative corners, that means that this product here is empty, but that empty product is not 0, the empty product is 1. So that's this one. And you can check that everything else here is there. Oh, I know, that's right. Yeah, it doesn't pass through the single base point, so there's no T. The sign actually is a plus, so we're good. A1 looks like something like this. So this looks like an inverse bigon. Those 2 corners. A3 is something similar. That, and then A1, A2, A3. Okay, and in fact, the way the things that I set up the orientations and such, all of these are plus signs. None of them pass through the base point, so just happens. There's another exercise to check, well, maybe it requires some more technology, but it is a fact that this thing looks like it could be in general some sort of infinite sum, but in fact it's not. So it's a finite sum. How are we doing? Yeah. Great. So for those of you who want a challenge, use this as an exercise. D of A5. So D of A5. So I'm going to write down what I got so you can check it against me and tell me that either you don't understand this or I'm wrong. Yeah, I think this is actually right. And I mentioned that I'm tempted to do everything in the non-commutative setting, so that's why I didn't lump the twos together. So what I've done is I just read the negative corners around in order around the boundary for this. But yeah, that's just my sort of nervous tick. You can combine those if you want. An exercise for the board. Okay, so that's sadly I've used 2 boards and I haven't actually finished the final differential, but we're almost there. So this defines the differential of any red chord, and I'm going to extend this to differential from the algebra vector itself by saying the differential of every ti to be equal to 0 and extending by the Leibniz rule. The sign is Leibniz rule. Which now makes sense because I've created everything. Okay, that's it. That's the definition of the differential. I'm feeling not too optimistic that I'll get to the geometric motivation at all today, so I apologize if that's the case. And if that is the case, then feel free to, I'm happy to talk about it outside of this. I think it's somehow to make contact with what we're doing in the rest of the lecture series, maybe it's good to focus on the combinatorial algebraic side instead. Okay, so results of the theorem is that d squared is equal to 0. And lowers degree minus 1 that. So that this actually is an honest differential on this algebra. And the second one is that under Legendre isotopy of lambda, this thing, which I guess I never actually said, but this is the Chekhov algebra, changes by well, the term that Chekhov uses is stable tape isomorphism. To avoid defining that, I'll just say by chain homotopy equivalence. It's actually something more specific than this. You get some sort of chain complex, but it's chain homotopy type is invariant under Legendre isotopy type. And so that tells us that if I take the homology of this thing, LCH of lambda, this is an invariant lambda under Legendre isotopy. And this thing here, this is Legendre. So two remarks. One of them is that this is so in the combinatorial setting, these were first written down and proved over Z2 by Chekhanov. But he was really inspired by some previous work of Eli Ashberg, which is not really, it's sort of written down. It's important to attribute Yasha also here. But in the setting that I've written it down here with signs and such, I guess this was written down in the paper of John and myself. Okay. So if I were to fill out this example, by the way, so D of A1, D of everything else. Let's see. But that has to be the case because each of these things here is in degree 0, and if it's the case that the differential lowers degree by 1, then it has to end up in degree minus 1, but there is nothing in degree minus 1. Okay, any questions about this definition? Yes.
So, in this general setting, are you assuming something about the field?
Am I assuming something about the fields?
Yeah, like, is it C2 or not necessarily? It's just,
It could be the field could be anything. In fact, the field has not shown up in this definition anywhere.
Oh.
So what I actually did was I defined something over C, but for the purposes that we're going to be using it for, you can just tensor your favorite fields.
Oh.
Other questions? So I wanted to make one remark, which I will not write down, but d squared equals 0. So in this particular example, and in a lot of examples like it, like for instance, the ones that come from rainbow closures of positive grades, it turns out that all of the generators, just like here, are in degree 0 or 1. And so it just turns out that d squared has to be 0 just for degree reasons. So there's like nothing to check. So in case you were concerned that maybe this is a tautological statement, it's not. So there's an example over there where d of something is d squared of a1 is equal to 0, but for non-trivial reasons. And so you can stare at that if you want. This is also going to make another point, which is that so you might be people in Heegard-Fleur and other sorts of flavors of Fleur theory might be more used to linear complexes that you get out of Euler theory. Where you have a, the chain complex is a vector space generated by some collection of generators. And the differential is on that vector space. So here we sort of took pains to take an algebra and not a vector space. So that's somehow that seems like that adds a lot of complication, but it is actually necessary. So there isn't, at least on its face, an obvious way to do this as a linear complex without doing some additional work on it. And this is another example of that. So if you were just looking at a linear complex, so maybe you would just only count things with a single plus and a single minus, and say the differential of this involves that. And if you do that in this case over here, I think you would get d squared of a1 is actually non-zero. Because d of a1 includes a2, and d of a2 includes a4. But there isn't another canceling term to that. So the term that cancels that actually comes from this quadratic term in the differential of a1 and this constant term in the differential of a3. Um, But what I will spend the rest of today talking about, something that Renee mentioned, these are augmentations. And what we'll see is that augmentations, so I'm going to define them in terms of the Trigonometry differential graded algebra. But what we'll see in the second lecture, and you'll probably see quite a bit before that, is also that they are closely tied in with fillings. So fillings of Legendrian links will produce augmentations, and that's sort of a geometric way that you can think about it. But for today, we're going to do these algebraically. So here's the definition. So maybe I should preface this by saying, okay, so in this comparison with other Floer theories that are linear complexes, the downside of Legendrian compact homology is, compared to some other non-homologies, is that it's not a complex of finite dimensional vector spaces. So if you think of this as a complex, the algebra itself is usually infinite dimensional, even in each grading. Like for instance, in the example that we gave, in degree 0, this algebra is generated by a1, a2, a3, and powers of t. And so you could take any word in all of those things, and that is a perfectly good generator if you think of this as a vector space of your fields. So this is an infinite dimensional thing. So that's sort of, if you are used to linear homologies and you want to compute the homology of this thing, that seems hard. There's a plus side though to having an algebra structure, which is that you have this multiplication, and multiplication allows it. So we're going to leverage this multiplication to construct these things called augmentations. So definition, augmentation. One of these differential graded algebras is, so I'll say it as succinctly as possible first. So it's a differential graded algebra map. I'll write as epsilon. To the field. So the field, I think of this as a complex with a zero differential on this. So this itself is also a differential graded algebra. So K is an algebra over itself, and the differential is just zero. And I should say, what's the grading on here? This is in grading. Okay, so that's a specific way to say it, but maybe a better way to say this is, in other words, it's a graded algebra map such that this committed with differential because this composed with the differential is the differential composed with that, which is just evident. And what does graded mean over here. So this means that epsilon of, for instance, AI has to be 0 if AI is in some grading that's not equal. Just because K is completely in grading 0, so if this is going to be a graded map, then it has to send every generator of the algebra that's in non-zero grading to.
Yeah.
What I'm going to do is I'm going to write log of lambda. This is going to be the collection of augmentations. Um, and I'll just note that so an augmentation of a lambda is determined by uniquely determined where it sends. Well, so it has to, so where it sends the generators, because it's supposed to be an algebra map. And what that means is that where it sends the AIs, or AI actually being in zero grading, and epsilon TJ for every data that's also in zero. Okay, any other generator has to be set to 0 for grading reasons. And these are all the generators of this algebra. So what that means is that you can think of the augmentation, so log of lambda, the set as sitting inside of k to the m crossed with kx to the r, where m is the number of degree 0 radicals, and r is the number of points. Actually, sort of implicitly assuming that every component has rotation number 0, so this is already satisfied. Okay. So it's a subset inside of here because it's just determined by where it sends each of the degree 0 ripcords and where it sends each of the t's. So let's do it in this example here. So the triple example, so I have now erased the differential of A5, but the differential of A4 is the one that matters. So if we have an augmentation, that means that if I plug in A4 into this, I better get 0. And so what this tells us is that epsilon of this thing has to be 0. And I didn't say this, but it was supposed to be implicit in the algebra map over here that epsilon of 1 is supposed to be 1. So it's epsilon should be the identity of the base field. So what this is this is 1 plus, I'll write it as x plus z plus x, y, z, where x is epsilon at A1, y is epsilon at A2, and z is epsilon at A3. So those are all elements inside of the fields. And this condition, this polynomial in x, y, and z has to be equal to 0. So an exercise is that epsilon, so epsilon is an augmentation of the trefoil. If and only if, so with this notation here, 1 plus x plus c plus x, y, z equals 0, and I suppressed it, but there was the T generator also appeared in the differential A5. And that shows up here as well, but all it does, the only additional condition you get here is that T has to be satisfied. So that, what that tells us is that the augmentation, so aug of the trefoil is. So since T has to be set to -1, that encodes no information. The interesting stuff is inside of K cubed. And you can run this computation for a general Legendrian link, and so what you will see is that epsilon, so the differential of every degree 1 breakpoint will give you some polynomial equation that has to be satisfied by this augmentation. And so what you're looking at is the vanishing locus of a collection of polynomial equations, and so for that reason, this is often called the augmentation variety. Questions about this?
Like the T, like in this case, the T album really see like when to find it.
Yeah, so if you do, the easiest example where it comes into play is the half link. So if you do the half link, there are two T's and their product has to be +1 for it to be an augmentation, but also the value of the augmentation at T is related to the value of the augmentations of the two breakpoints in the half.
How is that? So, what do you think?
Yeah, so it's something like, so for the augmentation of variety for the hop link, it's something like x, y, t1 and t2, such that t1, t2 equals 1, 1 plus xy is equal to t1. And this is inside of a squared plus b. Implicitly, there's something in here because T1 has to be non-zero. This is some condition on x and y. Right? This will come up again when Roger is doing cluster things. Great. So. So a few minutes left, so I wanted to say a couple of things. So here's a result. The augmentation variety of lambda is an invariant with an asterisk of lambda under Legendre Mascot. That actually is not an invariant under Legendre isotopy, for the reason that this depends on more than just the chain homotopy equivalence type of the underlying DGA. Depends on something about the where the generators live. So this is, if you want to make this precise, it's true up to products. Okay, so if lambda 1 and lambda 2 are Legendre isotopic, then I might have to take products with some factors of just K itself. And then these are the same as in sort of affine variety. You can make this more precise. So instead of this is sort of a loose statement, but there's actually a better way to say this, which is there's some notion of when two augmentations are actually equivalent, which maybe I'll talk about a little bit in the second lecture. And then instead of just looking at this thing, which we sometimes call the naive augmentation variety, you look at what's called the augmentation stack associated to this, which is this modded out by some equivalence relation. And then that thing actually is an honest Legendre speculative variance. We'll write it down. But this is already enough to distinguish, so sorry to scoop Berger's second lecture. But one way that you can show that the two Chekhanov this one here. That I did, I think it's all right. All right, two examples. So these two are not the same as each other. And if I gotten this right, this one, the augmentation variety, it looks like 1 plus x times 1 yc 0. So since and here the augmentation variety looks like 1 plus xy equals 0. That's b squared. And I'll leave it to you as an exercise to check. It's an algebraic exercise that you can't. There's no products of k's that you can multiply these two things by so that you get the same. So this is not the canonical way that one uses Legendrian contact topology to distinguish these two things. That involves what's called linearized contact topology. But since we're talking about the augmentation variety, again, let's check this. And maybe I'll just leave you with one more exercise in case you want more problems to, which also relates to an example that we gave before. Let's see. So one of the exercises I gave before was to calculate the differential for A5 over there. And the tricky thing is that, so I mentioned that you're counting a bunch of immersed disks, but some of the disks over there are actually honestly immersed, they're not embedded. But here's an example of a version of the trefoil where all the disks actually are embedded. So another version. Trefoil. By version, I mean just it's a different projection of it, but it's actually is the same Legendrian knot. 1, 2, 3, 4, 5. Nope. So this, I think, as Rajay mentioned, this actually is another version of the trefoil. It's the satellite of positive rays with 5 crossings on it onto the standard Legendrian knot. And the exercise is to check this as augmentation variety is isomorphic to the same thing. So it's 1 plus x plus z plus x1c equals 0. I think there is some products of just sort of trivial factors on here. So so this result says that it has to look like this, maybe, but in fact it's this actually. And the nice thing about this version as opposed to that one there is that in fact in this case all of the disks are embedded, so they're a little bit easier to see. The trade-off is that there are more wavecords to keep track of. All right, any questions about this? All right, this is an excellent time to stop. So I think again, so there will be a pause. I think my second talk is scheduled for Friday, and what I want to do then is talk about the relationship mainly between augmentations and fillings, but also maybe some relations to sheaves. We'll see where we get.